welcome back to ECE 441A, 541A. As people are turning in their labs, let me make a clarification if it wasn't clear. The labs are due today, but some people, I think, are getting confused with what I was calling a nominal mass. You need to include the weight, the mass of the carriage in addition to the plates. So if you haven't done that, you can correct your lab and resubmit it. I think I brought the old ones that have been turned in, I believe. So if you want to collect that, that's fine. But you need to include the carriage mass, which is another 500 grams or half of a kilogram. Everything's in kilograms. If you had 2 plates, that gives you 1 kilogram plus your carriage, giving you another 0.5 kilograms for a total. What I was thinking was clear was the nominal mass. The reason I said nominal is because we aren't weighing those 500 gram plates. They're roughly, so they're nominally 500 grams. We're just saying they're 0.5 kilograms. But if you have that correction or not including the carriage mass will obviously mess up your natural frequency when you compute K. So if you can quickly change that M and change a few numbers, I think, before you submit or even after you've submitted. If you've submitted it online in the Dropbox, I think I've provided you the ability to submit additional, and we'll just look at your most recent submission if you need to resubmit that. And if you can't do it by midnight tonight, don't stress over it too much. Although there's not a game tonight, or anyone in the emergency room for the game results, but that was a good result, so we should have smiles today. And homework 3 is not due tonight. Lab 1 is. Exam 2 is due in a few weeks. And today what I want to do is continue solving these differential equations, systems of linear equations that we've been representing in state space form. They have the A, B, and C matrices, meaning we're going to let B be 0, which implies that we have a strictly proper system. And we'll recap the scalar case just to get our minds going. We'll then go into the vector case. We will look at one piece of that solution, which is this e to the AT, this exponential matrix, and that occurs a lot. We call that the state transition matrix. We'll look at computing that with paper and pencil. I was in a hurry to get over here and I forgot all my attachments. I don't know if I'm going to do it on a calculator, but I might write down the commands that you can do it and maybe save yourself a little bit of the meticulous details that you have to go through. If you have these nicer calculators, you might as well use them. They'll do the symbolic matrix inversion for you. And on the exam, when you have to do that for a 10 by 10, just pushing a button might be easier than trying to invert that 10 by 10 matrix symbolically. That was a joke. Man, tough crowd. Once we get through that, the state transition matrix, we will connect the pieces. In that state transition matrix, we are going to see that the eigenvalues are very important. They are going to be appearing in these exponents of our exponentials, and those are going to be floating around all over in our state transition matrix. And those eigenvalues of our system matrix are consistent with the poles or the denominator roots of our transfer function. If we have a single input, single output system, it's just the denominator. We can find those roots, and those roots will be the poles of our system, which are also the eigenvalues in our system matrix. And we'll try to make all of those connections. We'll get started with a quick movie, meaning I'm just going to scroll through this fairly quickly. This is a recap of the scalar case, which is simply x prime is equal to ax plus bu, y is equal to cx. It's time invariant, which means we are considering A, B, and C to not be functions of time. Those are constants. That's a first-order differential equation that's potentially forced with an input u, where u could be a ramp, it could be a constant, it could be a sinusoid. It's not the unit step necessarily. U of t is the generic variable name that is assigned in a lot of control environments. And so just realize from context that that u of t is a general or a very general waveform or signal. We Laplace transform that first order differential equation, which is pretty straightforward. We just have to keep track of the initial condition if we're wanting the complete or total solution, and that appears automatically by the Laplace transform of the derivative. We collect terms and solve for capital X of S, which is the Laplace transform of what we're wanting to find in the time domain. We're trying to find little x of t. And now what's the state transition matrix? If you were to inverse Laplace transform 1 over S minus A, what would that produce? And the answer is there since I've scrolled through the movie so quick. If you can identify what we were calling the state transition matrix before, what is the inverse Laplace transform of 1 over S minus A? E to the AT. So if we write that in, and if A is negative, let's say we had x dot or x prime is equal to minus 3x plus u, then we actually have an A matrix that's minus 3. Our eigenvalue is just the A matrix. It's minus 3. That's in the left half plane. We have an e to the minus 3t appearing in this expression for our time domain response, x of t. We have the initial condition piece, and we have a piece due to the forcing function or the input waveform u of tau. And that's going to come into our system through the state transition matrix convolved with that time domain waveform. Meaning, if you have particular modes, and we'll talk about modes in your state transition matrix, those get influenced by the modes of your input signal. Those can be completely different. You could have exponentials in your system, and you could be exciting your system with a sinusoid. And u of t could be sinusoidal. It wouldn't even have to be decaying exponentially damped sinusoids. You might just want it to be oscillating. Here's the vector case. This is where we want to pick up today based on what we have just sort of recapped from before. The vector case, now we've just transitioned into capital letters. Now the A matrix is square. It's little n by little n in dimensions. B, we'll typically be using single input, single output. So the capital B matrix is n rows tall, 1 column wide. It's n by 1. The output matrix C is a short, long vector. It's a matrix. If it's a single output, it's 1 by n. And you can visually see the dimensions of these A, B, and C matrices, hopefully, in this vector case representation. Again, we're assuming a time invariant system, which means that the matrices are constant. We don't have values or parameters or elements in our matrices that are varying with time. If we simply redo what we have done in the scalar case in order to solve, we're now trying to find n, little n, Nevada expressions. We want an x sub 1 of t as a function of time. We want an x sub 2 of t as a function of time. We want to know what are each of these variables, state variables, doing. The state variables in the lab are position and velocity. In a general system, it might be position, velocity, voltage, current, pressure, temperature. You might have all of those as state variables, and you want to know what are they doing as a function of time. If we Laplace transform this vector differential equation, it looks very consistent with what we have just done. We have s, which is a scalar, but it's the frequency variable, times capital X of s, and now this, if you can see it, it's now tall and thin. This is a vector of Laplace transformed quantities, minus x of 0 minus. The same that is. That's now a vector of initial conditions. You have the initial condition on the first variable or coordinate in that vector. You have the initial condition at time 0 minus for the second and the third and the fourth, depending on how many state variables you have in your system. Those are all organized into that one initial condition vector. So that's just Nevada tall and 1y. We Laplace transform capital A x of t. The a is a constant. That factors out a Laplace transform. We Laplace transform little x of t, and that becomes this capital X of s. The same process can be applied then to b times little u of t, which when Laplace transformed becomes the matrix b, which was constant, times the Laplace transform of u of s. And u really could be a vector. We could have 4 different inputs that we're applying, and we know where those might be if we had a translational mass spring damper system. We might have many different input forces, for example. We could then Laplace transform the output equation, which is it doesn't have dynamics. This is just a linear relationship between the state variables x and the output y, and you can think of y as how your sensors might be combining the state variables to create an output signal. And it might be your sensor, for whatever reason, might be built or physically created in such a way that it measures position plus 1/2 of the voltage of some voltage quantity, and that's now y sub 1. That would be an interesting sensor, but that could be the sensor that you have, or it might be a signal that you simply want to keep track of. This is now times c times x of s. Now the only thing, well, the main thing now to obtain the solution or to solve for capital X of s that differs from the scalar case is now we have a scalar frequency variable s. This is just a variable, complex number, frequency, but it's times a vector. And we would like to factor or combine this term, x of s, with matrix A, capital X. And A is a matrix, it's square. And in order to make it compatible with the other term on the left-hand side, we are actually going to introduce this identity matrix that's the same dimension as our system matrix A. And that hasn't changed the product of S x of s. We have Si x of s, and that gives us exactly the same vector s times x of s, but this placeholder I allows us to combine. On the left, we now have Si minus A, which we can now factor out the Laplace transformed state variable on the right. Let's go ahead and move that initial condition vector to the right-hand side of the equality. And now we're in pretty good shape. The other thing that we have to keep in mind or keep track of is now we're dealing with matrices, and we can't just be shuffling the order with which we multiply matrices. Matrices in general do not commute, which means x times y does not equal y times x in general. What we want to do is isolate capital X of s on the left, and that means what's pre-multiplied both sides of this expression by the inverse of that matrix that's scaling x. And the matrix that's scaling x is now this matrix that has a variable. It has our frequency variable in it. So this is now a matrix inverse with a complex frequency variable included in it. So now we have to have a matrix inverse that's symbolic. We have to keep track of that S. It's not just a numerical inverse. We have to keep track of that S, but that S now is around, or just right on, concentrated on the diagonal until we start inverting that matrix, and then it gets thrown everywhere. But we also then have to invert or multiply on the left the second term, which is now Si minus A inverse B times U of S. If we now inverse Laplace transform that Laplace transformed equation, this Si minus A inverse is actually going to be consistent with how we did it in the scalar case. 1 over S minus A in the scalar case is really what you're looking at now in the general vector case. You now have an Si minus A inverse. So you could sort of think of this as 1 over S minus A. And how did 1 over S minus A inverse Laplace transform? As an exponential. It was e to the AT. Well, now we have that same expression. We just have to keep track of. Now in our exponent is this n by n matrix. And that now scales, or is weighted by, or the initial condition vector weights all of these interesting expressions in this matrix exponential. And we'll go through what that looks like in a minute. That's the first half, where we're now reminding ourselves that this is now the state transition matrix, which also appears in the second piece inside this convolution integral, because we now have two functions of S that are multiplied in the frequency domain. When we inverse those or take those into the time domain, now we have a convolution in the time domain. And the convolution will involve this state transition matrix. We now are integrating from 0 to t of e to the a t minus tau. T minus tau is simply a scalar. B u of tau d tau. Again, we can see that we actually have the two pieces to our total solution. We have one piece, or part of our response, due to the initial condition. We'll call that the initial condition response. If we didn't drive this system with an external input, we would only have that first piece, the initial condition response. If our initial conditions were 0 and we forced the system with an input, then we would have this forced response due to our input excitation signal, which is u of t. That's now the time domain expression. That's the solution to this 10 by 10 linear system of equations. We might have 10 state variables. If you plug it into this formula, boom, there's the answer. Don't you wish your differential equations class was that easy? All you have to do is remember this, or memorize this. Of course, then you might have to invert that 10 by 10 matrix. Try that after a little sleep after a big game, huh? That's why you need to make sure you're sleeping prior to exams. So hopefully we won't have any exciting games before No more Thursday games, right? This season. Who knows? We're engineers. We're not paying attention to football. Where were we? We want to now find the transfer function. If we now find the transfer function, that's now a frequency domain expression. We don't have to use this little x of t. We can go back and find our transfer function from this transformed expression in red, capital X of s. But the transfer function is between the input and the output. That red expression tells us how the input gets integrated into the state vector. To obtain the relationship between input and output, we then need to remind ourselves the relationship between the state vector and the output vector. That was simply y of s was c times x of s. If we now replace x of s with that expression above, we now have c times si minus a inverse x of 0 minus plus c si minus a inverse b u of s. But if we're wanting the transfer, this would give us the total solution of our output if we inverse Laplace transform. That would tell us what y of t is for all time, based on initial conditions and forcing function u. If we just want the transfer function, we're not interested in, or we don't need to worry about the initial conditions. And that's what we want. We want the transfer function from this expression. We did it fully so that we could sort of see what was going on. But if we're wanting the transfer function, we can simply set the initial conditions to 0. Doing that says now that y of s is simply c times si minus a inverse b u of s, and the transfer function is right there looking at us. Here is our transfer function of our system between the input u and the output y, g of s. Questions on that development? That's just sort of, we have that information. Now what we want to do is learn a little bit more about this state transition matrix. Try to get a little bit better feel or insight into this matrix exponential, this e to the at. What is that? What does that look like? And now we need to rely on our linear algebra machinery or knowledge. The A matrix. If somebody gave you a square matrix and they said, find the eigenvalues, you're going, why do we need the eigenvalues? Now we're going to learn. That's critical for the dynamic behavior of our system. Let's now look at the state transition matrix. From our equation, y of s, we had the state transition matrix actually appearing a couple of different places. We had c, si minus a inverse times x of 0 minus, plus we had c, si minus a inverse b u of s, and the state transition matrix that we're interested in is this piece that's consistent or appears in both parts of our two parts of the total solution. This piece that I've now identified in red, we want to actually inverse Laplace transform that. Now I didn't give myself enough room, so I'm going to erase that. We want to now look at the inverse Laplace transform of si minus a inverse. the SI minus A inverse is really the frequency domain version of our state transition matrix, and the time domain is what we now call the state transition matrix, and that's this E to the AT. And sometimes we might, or the textbook might actually refer to that. Maybe they don't like to typeset that. They don't want that matrix up in the exponential. They may just call it something else. They may just say the state transition matrix is maybe just called capital phi of t. They tried to put some Greek in here. So now we have capital phi of t, but that's just e to the AT. When you're learning new things, how many have seen the state transition matrix? How many have had to compute e to the AT as a matrix? Few brave souls are willing to raise their hand. Let's talk about what it is not first, so that you don't, on an exam in haste, go, oh, that's e to the AT, I know how. Let's show you what e to the AT is not first, and then we'll learn how to compute it. E to the AT is not the following. So make sure you write that sentence down before you write the rest, and you go, well, that's what Tharp told us. It was just this expression. Let's say that you now have a matrix A that is minus 3, 1, minus 2, 0. I'm saving the bigger ones for your exam. Here's a 2 by 2. Okay? What e to the AT is not, maybe you can guess. You don't just raise each of those elements to the matrix to the exponential. You don't build your matrix exponential by simply element-wise forming the exponent. It's not equal to e to the minus 3t, e to the 1t, e to the minus 2t, e to the 0t. That is not what this is. Okay? Not. Okay? You can't just do that. It's a little bit more interesting. Okay? So now let's define or just state what the matrix exponential actually is. So the definition, does everybody remember the expansion? The Taylor series expansion of just a scalar exponential. Well, it follows over really structurally when A, the exponent, is a matrix. Now it's going to be the identity matrix. How big is I? Just if you had to guess. Depends on A. Good answer. What if A is 3 by 3? How big is I? It's 3 by 3. I is the same dimension as your A matrix. Now we need to keep going. We take A times T. T is a scalar, but it weights this 3 by 3 matrix. Then we have plus A squared T squared over 2 factorial. And there's the pattern. Plus A cubed T cubed over 3 factorial. Plus dot, dot, dot. And that just keeps going. Meaning, if I give you a 10 by 10 on the exam, it may take you a while to compute A to the 6th times T to the 6th over 6 factorial. But that factorial grows fast, doesn't it? So those terms start to vanish in a little bit, and this is a very poor way to numerically compute the matrix exponential. So we want to do it by paper and pencil, a different way. And we're going to do it using, starting the frequency domain. We know what the matrix exponential is. It's SI minus A inverse in the frequency domain, and we know how to inverse Laplace transform. So let's do our matrix inverse in the frequency domain, and then inverse Laplace transform all of the little terms that result, each element. What is he saying? So here's our paper and pencil strategy. Since you don't have anything to do this weekend, there aren't any games to worry about, you can play with this. Okay? You can take out a 10 by 10 matrix. You can just trade them back and forth. You can just exchange square matrices, 10 by 10, make some up, but you know how to create those. Write a circuit. How many energy storage elements do you have in your circuit if you want a 10 by 10 matrix? You need 10. So now you have 10 inductors, let's say, and maybe 20 resistors floating around. Solve that circuit, and now you have this system of equations. You have an A matrix. Now you can find the matrix exponential. I know you're just waiting to get home to try this. So let's now do the inverse Laplace transform of SI minus A inverse. That's how we want to do it on paper and pencil. Or you might see this as phi of t is e to the at is also this inverse Laplace transform of SI minus A inverse. Or somebody might want to just write that in the frequency domain, and they may say, well, I know what capital phi of t is. What's capital phi of s? It's just what's inside that curly bracket. That's the Laplace transform of the earlier. So this is now the Laplace transform of phi of t, which is just SI minus A inverse. What I'm trying to say is SI minus A inverse is the key. We need to find that. That's a symbolic matrix inverse. If we can find that, then we can inverse Laplace transform each of the 100 elements in our 10 by 10 matrix. So maybe tonight, maybe you'll do a couple of 10 by 10 inverses, because it involves 100 different Laplace transform inverses for each of the elements. You thought you were up late for the game. All right, so let's look at an example. Suppose that x1 prime and x2 prime, we have a second order system that are governed by this system matrix dynamics, -3, 1, -2, 0, and let's say that the input matrix is 2, -1. Whoa, whatever happened. We now want to find the matrix exponential phi of t, which is now the inverse Laplace transform of SI minus A inverse. So now that's going to be the inverse Laplace transform of what matrix? How big is my identity matrix? It's 2 by 2, and I have S's on the diagonal. I now have S in the 1, 1 entry and an S in the 2, 2 entry. I simply have to subtract the 4 elements of A from those 2 diagonals and the 0 off diagonals. So that SI minus A as a matrix is now S plus 3. In the 1, 2 entry, I subtract 1. In the 2, 1 entry, I subtract -2. And in the 2, 2 entry, I have S minus 0. I need to invert that matrix symbolically before I can inverse Laplace transform that. But if you had one of these TI calculators that does symbolic math, you could simply say, oh, I need to build up a matrix, And on the TI-89, it might be easier to use the X because that's a built-in function. If you have the TI Inspire, you can just use the lower keyboard and use the S. And then it's pretty easy. If you have the TI Inspire, you can just plug the S. You can just say S. And then you can say something like times. Now build up a matrix. Boy, are your eyes better than mine, I hope. You now do a matrix, and you say, this is SI, so I now have 1. Where did 1 go? Didn't I hit it? Oh, you silly thing. That's why I wanted the... That's why I needed to bring my keyboard, and I ran out of my office so quick I forgot it. But now I have 1. Now, where's comma, 0? Now I need to do a semicolon. Oh, brother. Wow, I remembered that. Get in there. And then we have, next time I won't forget that keyboard. Boy, this is tricky. But it's not that bad if you, and then you hit enter. And there's the SI minus A. So that's what I want. I want to now, in the TI, you might say, you just do it all. You say x plus 3, comma, minus 1, semicolon, get you into the next row. Then you do 2, comma, x, and then you do this caret, raise that to the minus 1 power, and you're good to go. Is that clear? And then it has the matrix inverted for you. Or over here, if I now said something like, oh, I don't know why I'm playing with this, but this is kind of fun. You now have A defined to be another matrix, which is the matrix in question, which was, what was the matrix in question? Minus 3, comma, 1, semicolon, and then it was minus 2, comma, 0. Was that my matrix A? Don't want to have to re-enter that. Then I could simply say something like, go up and enter that SI minus A, then say subtract minus, and then go up again, pull down the A, and now I have SI minus A. Is that right? That should be what I wrote down right here. S plus 3 minus 1 in the top row, 2 and S in the second row, and now that's what I have in my calculator. What I want to do now is simply invert that. So I go up and copy it, and then I say raise that to the minus 1 power. See how quick that was? So let's do that by hand. Now we want to inverse Laplace transform that matrix symbolically. But how do we invert a 2 by 2 matrix? It's actually not too difficult. We take 1 over the determinant. The determinant is 1 over the product of the diagonals minus the product of the off diagonals, and that's minus 2. And now what do I have in the 1, 1 entry? Well, if I did it the long way, I would eliminate the first row, I would eliminate the first column, and I would take the cofactor of the matrix that remains. Well, the matrix that remains here is just a scalar. That's S. And I weight it by minus 1 raised to the 1 plus 1 power. To find the adjoint or the cofactor matrix for the 1, 2 entry, I now eliminate the first row, the second column, find the determinant of what's left, which is just 2, weight it by minus 1 to the 1 plus 2, and that's now my top row of the cofactor matrix, because since I need the adjoint matrix, I need to transpose that. Is this making sense? For a 2 by 2, you just interchange the diagonals and negate the off diagonals and you're done, but I'm doing it the long way. Now to obtain this one, I have a minus 1 raised to the minus 1 to the 2 plus 1 power. And down here I have, removing the second column and the second row and taking the determinant of what's left, I just have s plus 3, scaled by minus 1 raised to the 2 plus 2. And if we do all of that, we now have the inverse Laplace transform of 1 over s squared plus 3s plus 2. I have s times 1. I have minus 2. Oh, can I go ahead and transform or transpose that? So that minus 2 is going to go down here once I've transposed that. My 1, 2 entry there in the row that I haven't, that was completed, is minus 1 times a minus 1, or a 1. Transposed goes up to the 1, 2 entry. And the 2, 2 entry transpose stays put, but it's now s plus 3. Are we okay with that? So that now, if we simply look at this, I now have a 2 by 2 matrix. In the first, in the 1, 1 entry, I have s divided by the determinant. In the 1, 2 entry, I have 1 over s squared plus 3s plus 2. In the 2, 1 entry, minus 2 over the determinant. And the 2, 2 entry, I have that. Questions on that? That's now the SI minus A inverse matrix. We now need to inverse Laplace transform each of the 4 elements in that matrix. And we can then, and in doing that, what are you maybe queuing on? You might like to know, what are the roots of the denominator? Are they real? Are they complex? In this case, I think we can actually factor that mentally. We have s plus 1 times s plus 2. But if we couldn't see that, if it's, you know, an intense time during the exam, you could say something like, oh, do I want to find it? Let me see if I can find it. What if I go to the complex, quit. Sorry, talking to my machine. Not you guys. You guys do not quit, okay? You just keep going. I want the complex zeros of s squared plus 3s plus 2. And I have to tell it what the variable is, which is s. Whoa. Which is comma s. So it's minus 2 and minus 1. Now we need to do the partial fraction expansion on each of those terms. But we have a calculator. So let's just go and say, you know what? Let's use the expand function. Since I know I have real roots, this will work. Oops. And let me copy that down into my expand and hit enter. There's my partial fraction expansion. 4 different pieces. Pretty quick. Now you just have to make sure that you keep track of things, but now that's telling us a lot. When we found the roots of that denominator were minus 1 and minus 2, what do you physically start seeing or mentally start thinking about? It's stable. In the time domain, what are you seeing as far as modes or expressions? You now have these decaying exponentials, right? E to the minus t and e to the minus 2t. And this matrix, this state transition matrix, is simply going to be a collection of those decaying exponentials. If you inverse Laplace transform, let's look at the 1, 1 entry. We now have 2 over s plus 2. We need to inverse Laplace transform that. And we have minus 1 over s plus 1. The 1 over s plus 1, how does that inverse Laplace transform? E to the minus t. That was pretty easy, wasn't it? It's a good thing you learned your 320, isn't it? Boy, who did you have for 320? Oh, I thought you were going to say... Dr. Dvorak, I'm going to go shake his hand today. Good. I was hoping you would say me. Oh, well. Live and learn. Good. Good. So you know how to inverse Laplace transform these real roots, or these real frequency domain expressions. If we do that now we can do that here. What did we just learn? We found that the inverse Laplace transform, we could do this the longhand way, but we just found that that's 1 over s plus 1 plus 2 over s plus 2. And we had 1 over s plus 1 plus a minus 1 over s plus 2. We have a minus 2 over s plus 1 plus a 2 over s plus 2. And you should just be seeing mentally these decaying exponentials as you're writing this down. And so there is something to be said for writing that down. So that now your matrix exponential, your state transition matrix, e to the at, is what? It's minus e to the minus t plus 2 e to the minus 2t. That's one of your 4 entries in your state transition matrix. Your 1, 2 entry is e to the minus t minus e to the minus 2t. Meaning, this state transition matrix tells you how your system evolves from one time instant of your state to another one. As t gets bigger, this tells you how you transition between, let's say, a position of 10 and a velocity of minus 1 to some new state value. And this tells you how that will happen. The second row you've already completed. It's minus 2 e to the minus t plus 2 e to the minus 2t, 2 e to the minus t minus e to the minus 2t. Wasn't that easy? Especially if you had that buddy right there, right? So now you can go home and convince your parents that you need to spend $150 or whatever for a calculator. So you can invert a 2 by 2 matrix. They're going to go, come on, go old school. It's good for you to do it by hand. Mom, really? Yes, we can do that. Sit down, son. Let's invert that matrix. 2 by 2. Now, what's that give to us? Well, if somebody now gives you an initial condition, you now know exactly how that initial condition is going to propagate through your system, especially if you don't excite it with the external input. If somebody gave you an initial condition of 4 and 7, what's going to be your system response? Initial condition response, I didn't say anything about an external input. U of t, I'm saying is 0. What is x of t? You remember, right? You're just playing with me. I took my glasses off so I can't see your faces. You're kind of smiling, grinning. What do we have? This is just It's e to the at x of 0 minus. And we just computed x e to the at. Do you see now what's going to happen? If I wanted to know what x1 of t is equal to, it's going to be the 1, 1 entry of my state transition matrix times x1 of 0 minus plus the 1, 2 entry times x sub 2 of 0 minus, and this was e to the minus t minus e to the minus 2t times x sub 2 of 0 minus. But this guy we just said was 4, and this guy we said was 7. And now you have your initial condition response for the first state component, and what is it? It's some linear combination of those decaying exponentials that came about from the eigenvalues of A. The exponents are -1 and -2. That tells you a lot. Think about that, dream about that, just really mull over that this weekend, and we'll pick up somewhere close to there on Monday. Have a good weekend.